This is for Year 11 Specials. We're going to go over question 6b, and it's titled Proof by the Contrapositive. Okay. So we're going to learn about another proving style. So contrapositive proving style is different to 6a in that you're not doing a direct proof. Okay. You're still wanting to prove that P causes Q, if P, then Q happens, but we're going to do it in a slightly more indirect way, okay? But we still get the same result, or still a similar result, okay? So what we get is what we're trying to achieve, okay? So now, first of all, we're going to go through the negation of a statement, okay? This is important because this sort of ties into the contrapositive. Okay, so to negate a statement P, we write its very opposite, so not P. All right, so if we have P, then the negation would be not P. So that's the negation. Okay. All right, so here's some examples. So if I have a statement P, the sky's green. We know that it's originally false because the sky's not green. Then not P, okay, or the complement of P would be the sky is not green, okay, which is true. 1 plus 1 is 2, we know that's true. The negation, 1 plus 1 is not 2, is false. All prime numbers are odd, okay, we know that's false. Then there exist prime numbers that are even, so that's true. Okay, so when you negate something, a true statement becomes a false statement, and a false statement becomes a true statement, okay? So the triangle example I won't read, but it's the same idea. So we want to practice doing negations, okay? So here's example 1. We want to write down each statement, and we want to see which negation is true and which negation is false, okay? So first of all, is the statement 2 greater than 1 true? Yes, it is. Okay, is 5 divisible by 3? That's false. The sum of any two numbers is even. Sum of any two odd numbers is even. That's true. And there are two prime numbers whose product is 12. That's false. Okay. So then the second part of the question asks you to write a negation statement. Okay, negation, the opposite statement to whatever it says there. Okay, so 2 is greater than 1. So the opposite statement will be 2 less than or equal to 1. Okay. Now, just be careful with inequalities. If you're trying to do the opposite, like the not version of it, if it doesn't contain equal, the negation will be sign flipped with equal. If it does contain an equal, the sign flipped will be, the flipped version will not contain an equal. Okay. All right. So, and that's obviously false. Okay. So we'll write the negation statement and whether it's true or false or not. So 5 is divisible by 3. We know that's false. So 5 is not divisible by 3. So that's the negation statement. That's the not P statement, if you want to think of it that way. So that's true. The sum of any two odd numbers is even. So the negation will be the sum of two odd numbers is odd. Okay, so the negation part will be just the odd. Sum of two odd numbers is odd. That's obviously false. Okay, so I'll just write an F there. There are two prime numbers whose product is 12. There are no two prime numbers whose product is 12. Okay, and that's true. Okay, so that's basically how you, like a basic overview of like how you negate a statement. All right. So let's go to De Morgan's law. Okay, so negate. Okay, so when you're negating a statement with that involves and or an or, this requires De Morgan's law. Okay, so if it's not P and Q, then it's the same as not P or not Q. Okay, so in set notation, not P and Q and is the intersection. So not this would equal not P or not Q. So union not Q. Not P or Q. Not P or Q is not P and not Q. Okay, so that's the set notation version of it. But yeah, so if anything contains and or in the statement, you'll need to use De Morgan's law. Okay, so write down the each statement and its negation, which is statement, and its negation is true, which is false. Okay, so all right, so is 6 divisible by 2 and 3? That's true. Okay, 10 is divisible by 2 or 7. Okay, now you got to be careful here. The or is very inclusive. Okay, whereas and is not. Okay, so 6 has to be divisible by 2 and also 3 as well. But 10 can be divisible by 2 or 7. Okay, so it's leaving the option open. Can it be divisible by either one of them or both of them? And that's true. It can be divisible by 2, and that's all you need. Okay, you don't need to. It doesn't have to be divisible by 7 as well. Whereas this statement is more restrictive. It has to be 2 and 3. Okay, so now let's write the negation. So we're going to use, because there's an and there, we have to use De Morgan's law, and you get something like that as the final statement. Okay, so 6 is not divisible by 2, or you see the or, yeah, or 6 is not divisible by 3. Okay. Similarly, this is a or statement originally. So if you have an or statement originally, then it becomes an and. Okay, and the negation of it. So not P. So 10 is not divisible by 2, and 10 is not divisible by 7. Okay, now if we look at the negated statements, okay, is it true or not? Okay, so 6 is not divisible by 2, 6 is not divisible by 3. So neither statement's true, and even though it's conclusive, you need one statement to be true for it, for the whole thing to be true. But that's false because both are not true. 10 is not divisible by 2, and 10 is not divisible by 7. Okay, so with this one, because it's and, you need two conditions to be true for the whole statement to be true. So one condition's, yeah, so even though that condition's true, like 10 is not divisible by 7, that's correct, but 10 is not, saying 10 is not divisible by 2 is incorrect, because 10 is divisible by 2. So because there's an and tied to it, it needs to meet both conditions. Both conditions aren't met, so this is false. All right, let's go to the crux of the exercise. So it's proof by contrapositive. So let's go back to the statement. If it is the end of term, so that's your P, then students are happy. Q. Okay, so if P's true, then Q is true. So by switching the hypothesis, we negate both. We obtain a contrapositive statement. So contrapositive statement basically means we go backwards and we negate each of the original statements. So if students are not happy, then it is not the end of term. Okay, so if Q dash, then it leads to P dash. Okay, so really important that we know how to go from original statement to its contrapositive statement. Okay, so Q dash leads to P dash. Now, so the original statement and its contrapositives are logically equivalent. Okay, so if the original statement is true, then the contrapositive is true. If the original statement's false, then the contrapositive's false. Okay, that's important because that sort of underlines the idea of proving the original statement by its contrapositive. So this means that to prove the conditional statement, we can prove its contrapositive. Okay, now why would we want to do the contrapositive instead of the direct proof? Okay, remember this was part of exercise 6a. That's a direct proof. Why would we want to do this instead of this? Well, the reason is if we prove this, then this is true. Okay, so in proving this, you're proving this. Okay, because they're linked. So if we prove this and it's correct, then we've proven this also. Okay, we've proven it, so we don't need to actually do the direct proof. Okay, so sometimes this is advantageous because the direct proof is harder to do. So summarizing, the contrapositive of P leads to Q is not Q leads to not P. Okay, to prove P goes to Q, we can prove the contrapositive instead. Okay, so that's the key of the whole exercise. Okay, so let's do this. So consider the statement if n squared is even, so we'll call that P, leads to n is even, that's Q. Alright, so the contrapositive would be not Q leads to not P. Okay, so write down the contrapositive. So if n is odd, then n squared is also odd. Okay, so I've negated, so whatever Q, I negate it, so not Q, needs to not P. Okay, negation of that. So both of now these are odd. Now I'm trying to prove that if n is odd, so I'm trying to prove this statement, this contrapositive statement. So if n is odd, then n squared is odd. Okay, if n is odd, so let n be an odd number, 2k plus 1, and k be element of z. So that's n odd, right? Okay, so we're assuming that's true. Then n squared's odd, so n squared would equal 2k plus 1 squared, which equals 4k squared plus 4k plus 1. Now, how do I prove that this is odd? Well, I can make this even, prove that that's even, so that's 2, take a factor of 2 out, 2k squared plus 2k plus 1. Now we know that's even, and that's odd. So an even plus an odd is an odd. So therefore, we've proven that the contrapositive is true, right? Because we've proven that if n is an odd number, then n squared is also an odd number. So therefore, by proving contrapositive, that Q dash leads to P dash, P leads to Q. Okay? P leads to Q. Okay? And I've defined my P and Q in the question. Okay, so that's important. Okay, so you can't just write that abbreviated without defining it first. I've defined it, and I've proven that contrapositive is true. So by proving contrapositive true, the direct statement P leads to Q is also true. Okay, so that's done. Alright, so let's do another one, just to, really get this concept. So if that's even, then that's odd. Okay, so the contrapositive will be, so again, I'm going to define my P and Q, just so if P, then Q, then the contrapositive would be if not P, then not Q. Not Q, then not P. So not Q is if n is even, then n squared plus 4n plus 1 is odd. Okay, so let's start with the statement, the assumed statement, n is even. We're trying to prove that contrapositive, so n equals 2k, where k is the element of z. Okay, I'm trying to show that n squared plus 4n plus 1 is odd. whoops, 2k plus 1. That's 4k squared plus 8k plus 1. Is that correct? Yep. So again, I'm going to factorize these two. With a 2, take the 2 out. 2k squared plus 4k plus 1. So we've got an even plus odd. So that gives you an even. Okay, I might write down there because I want to show. So that's even plus an odd. So that's going to be odd. Okay. So therefore, by contrapositive, by proving contrapositive is true, so P Q dash gives you P dash, therefore P gives you Q, P leads to Q. Okay, so we've again proven the statement by contrapositive that since the contrapositive is true, then the original statement is true. Okay, so just summarizing very quickly, exercise 6b. So to negate statement, we'll write its opposite. Okay, so, and you know that, so P, to negate it, you go to not lead. P goes to not P. For a statement, P leads to Q, the contrapositive will be not Q leads to not P. That is, we switch the hypothesis and conclusion and negate both. A statement as contrapositive are logically equivalent, and by proving the contrapositive of a statement, it may be easier in some cases do this rather than doing the direct proof, that is P leads to Q. Okay, so doing not Q leads to not P is equivalent and is proves P leads to Q. Okay, so you might want to do that. All right, hopefully that helps. Have a go at the exercises, and if you need any help, obviously let me know so I can give you some. I'll make a video for you to explain the question.